audience, so I'm sorry if I wander around my arm, do what I can. I'm going to present you the ways to team up Django and web mapping, mainly to introduce you the fact that cartography and web mapping can be simple. So one of my goals is to show you that you can do cartography very easily with the Django toolbox. And I would have reached my main goal if you stop using Google Maps without knowing how it works behind the scenes. So that's the goals of my presentation today. I'll start with the fundamentals of cartography, just to make sure we gather everyone on the same level of knowledge. It might be very obvious and straightforward for most of you, but it's good to come back on those main concepts. I'll introduce you how web mapping works, how a map is built, and how it consumes data, and how it's structured on the web page. And for like the main components of Django, most of them come from the contrib keys and two applications I wrote at Machina Corpus, the company I work for, which thank a lot for giving me the opportunity to come here. The fundamentals of cartography might appear very obvious, but cartography is based on locations, and you get positions of the geometries on Earth using longitude and latitude, which is basically x and y, like any geometry you used to. The units usually used are decimal degrees, so the whole loop around the Earth is divided in 360 fractions, and the sub-fractions are floating numbers. So it's very simple. From west to east, it goes from minus 180 to 180 east, and from south to north, from minus 90 to plus 90. You all know that because you all have GPS, and that's the way it works, and you're used to see those numbers and those positions. But that's basically very important to know, and most of the people are confused between x and y and longitude and latitude. As you know, x and y is not on a flat Earth. We've known it for a while now. The Earth is not flat. It's not a perfect sphere either. So we use the reference is an ellipsoid, which is basically a sphere where the two poles are squeezed a little bit. So it's an ellipse. There are more complicated ways of getting references on the Earth, taking into account the shapes of the surface and everything. Today I want to show you that we can do cartography with very simple concepts. The reference is the one used by GPS since 1994, and it's an ellipsoid. The science of getting positions on the Earth is called geodesy. It kept busy scientists for a while, and it can be very complicated, but if you focus on just longitude and latitude and ellipsoid, you shouldn't care about all the rest. Cross-section, that's the little one, that's the little notion that can become very big problem, and that basically can confuse anybody. To be simple, it's just a set of equations to transform a position on the sphere, on the ellipsoid, to a position on a plane. So cartographers have used it for a while because they were drawing or printing maps on paper, and the sailors in the Middle Age or whatever we are using this paper to measure the distances, so it had to be very precise because they could lose many hours sailing if the projection was not right on the paper and everything. Now we're dealing with pixels, and we still represent the sphere ellipsoid on a plane. So representing spheric coordinates on a plane means you have to do some compromises. Maybe you will lose the proportions of the areas, or maybe you will lose precision. You have to do some compromise. The Mercator projection is the most famous one, is the one from Google Maps. It does a lot of compromises regarding areas. If you look at the Greenland on Google Maps, it's almost as big as Africa, whereas Greenland is not that big. It's just that it's very close to the North Pole and it's very extended and deformed. So representing spherical coordinates on a plane means doing compromises and changing from one projection to another. It's called spatial reference transformation. A spatial reference is just a very scientific description of the coordinate system you're using. So there are many parameters you can use. You can configure the base axis for, in case you want another axis than Greenwich and the equator. You can specify a lot of parameters, but I don't want you to get into those details. And just remember that we store the data. Oh, sorry, the orange doesn't show up very well. You store the data in WGS84, which is the one from GPS. The spatial reference ID is 4326. You display the maps using the Mercator projection, spatial reference, which is one from Google Maps. And the code is 3857. But still, you shouldn't worry about that because, for example, that's the default values for most these tools, especially Django. And I put them in the slide just so that you know, but you shouldn't worry about that either. And you shouldn't worry too much about projections because most probably your maps are going to be displayed on a small device, and you shouldn't worry about the precision of centimeters or millimeters or whatever. So those are fine. Those are fine. There are two kinds of data. Vector data, which is the most intuitive one. You have point, which has x, y, and an optional z coordinate. A line is another ordered list of points. And a polygon is an envelope, which is a closed line, and a set of optional holes, which are also closed lines. This is very intuitive, but that's the basic three objects you will use to describe the whole world and describe objects, geometries, and that's all you have to know about storing geometrical shapes and objects for cartography. The other kind of data is raster data, which is not as opposed to vector, which is a set of cells, like pixels. So you basically remember them as images, and that's it. Of course, you can think of them for displaying MATLAB backgrounds, but they also can store altimetry data, where each pixel will store the elevation of the terrain you sample. Raster data can also be stored in the database, and it can also be geo-referenced. The main difference with vector data is that you can't, you have a predefined resolution, that's it. It's like one value for one cell, and one cell can be as big as you want, or as small as you want, depending on the resolution, which is fixed in this case. A PostGIS database is very simple. There is nothing mystic about it. It's just an extension, as Mark told us. The activating extension adds new column types, the one we've seen before, point, line string, polygon, raster as well, since the new version PostGIS 2. And geographic functions, which will allow you to do special operations on the geometries, and also have spatial predicates, like does this shape intersect this other shape, or give me the union of this polygon with this other polygon, and this is like a PostGIS toolbox. The documentation is very rich and will give you hundreds of functions to manipulate geometries. Basically the same that you have in Inkscape or Illustrator, which I don't know very much, but like you take two shapes and say, give me the intersection, give me the subtraction, union, whatever. Special indexes are very important because special operations are costly. So special indexes will allow you to reduce the data set you're working on, and they are using trees of rectangles to reduce the extent of the map of the data set, and work on a small data set that is confined in this rectangle. They used GIS as the map of it. Installing PostGIS is very simple, and it just adds one additional step in the database creation process, which is activating the extension. And once you've done create extension PostGIS in your database, you've got access to all of these new types and functions and everything. I'm sorry, I'm gonna show you something very vulgar. Oh, it doesn't show well, but it's SQL. I'm sorry, I'm showing you SQL code to create a table, just to make sure that you understand it works exactly the same way. You define columns as usual, except that you have a special type geometry, where you can specify the geometry type and the special reference. That's it. Then you have the possibility. Can you read well? Yeah. You have the possibility to do spatial joins, which means you will join two tables on one special predicate. In this case, I'm looking for all rooms that are present on the island. So it's just a normal join, except that I'm using a special function that returns true when the two geometries intersect. To create new objects, new records of geometry, you can write also something called WKT, well-known text, which is a textual version of the geometry, and then you cast it to geometry and insert it to the table. Of course, you can use graphical tools, but I wanted to show you that it's very simple. Now that we've seen the basics of cartography, I want to show you how webmap works. So now that we know that it's very simple in the back end, I'm showing you some things for the front end. Leaflet is a very simple web mapping tool. It uses JavaScript to initialize some DOM elements and adds the layers, each layer on top of each other. And the background is just a set of images that are placed, aligned and placed as a grid. The vector data is rendered using SVG, Scalable Vector Graphics. The JavaScript receives the vector data and generates the SVG into the DOM, and the border just shows the geometry. Every latitude and longitude are transformed into pixels using SVG or CSS directly. And it relies massively on the browser to get the events of clicks, mouse over, and everything. And since it uses the DOM, the browser brings up every event to detect interactions and build interactive maps. I'm sorry, it's very dark. Leaflet is very simple. With these few lines, I just use the assets, JavaScript and CSS, define a div. And then with these few lines of JavaScript, I initialize the map, says that the view should fit the world. I add a tile layer, which is the background from openstreetmap.org. And then I add a simple marker at a specific location, latitude and longitude. And I get a simple map on the whole world with the marker in the middle of it. It's very simple. There are also other web mapping libraries. The most two famous are D3, which relies on SVG massively, but and allows very cool data viz and exotic map projections, which are very cool depending on what you want to show. And OpenLayer 3, which is for most use cases that are a little bit more advanced. The formats are very simple. The background images are PNG or JPEG. They're very simple. The zoom, it's like a folder tree of zoom, X and Y, which is like a grid, and the web mapping library will just download them, put them aligned, and the map background will show up. That's it. The projection is the one I told you before. If the data doesn't change, you can use a tile provider. There are many on the web. And if the data you want to put in the background comes from the database, you might need a rendering engine that will trace the database records into images and serve them as PNG or whatever to the web mapping engine. Regarding vector data, we use GeoJSON, which is the simple JSON, but with specific layout for geometries and properties. Very useful if you want to have interactions with the objects on the map. You might take care of the volume because GeoJSON is very verbose and can be very heavy to download. And depending on the frequency of changes of your data, you can control caching and whatever. It works exactly as JSON, and the JavaScript library will consume that and render as SVG. There is nothing new in that. Static images, PostGIS and Django to render the GeoJSON, and an optional rendering engine that will maybe overlay some RESTful data, but we grade this one. Django is a very rich ecosystem, and we use Django for the same reason we use Django. There are model fields that will create the database columns, geoquery set that will allow us to query the database, and form fields that appeared recently. And the only thing is that it's a little bit harder than usual to deploy, since you have a couple of system libraries to install, but that's it. There are also widgets in an admin side class, but it uses a very old web mapping library I don't recommend. The model creation is as simple as usual. You define the polygon field like you define the core field or an integer field, and you have a special geo manager that will allow you to write query sets that handle geometries. To create records, you can use the classes available in GIS and give the coordinates as tuples or even from string with the format I showed you before. You can also filter objects by intersections, exactly like PostGIS would allow you. I wrote Django GeoJSON to serialize the database records as GeoJSON very easily. It's a set of class-based views. It will serialize the record and with a set of options to either generalize the geometry, that means removing points to reduce the resolution, or maybe remove decimals because the 6 decimal is around 1 millimeter. So if you serve a GeoJSON with 12 numbers after ask what the numbers you like talking about, micro, meters, whatever. So you can just truncate the numbers. I also wrote recently model fields which fall back to JSON storage. That means you can have GeoJSON fields that will be stored as JSON in the database, so that you can have geometries without having to install hotkeys and the whole key stack. Very easy to set up and very useful when you have simple use cases. And the last one also is vector types for huge data sets. It allows you to split very huge vector data sets into little types that are unloaded and loaded when you move the map around, which prevents you from loading your whole data set if you just looking at a very small extent. And Django Leaflet, which is an integration of Leaflet and Django. Very easy to start. There is a simple template tag, you put it, and you have a map that shows up. The assets will be collected, and there is a very easy plugin integration. You can control the Leaflet plugins you want to add. There are many of them. The configuration is controlled in Django settings, which is very, very easy to choose the background layer from the setting, choose the default extent, maximum zoom, whatever. And it sets up for you all the projection machinery if you ever need it. This is an example of loading the GeoJSON layer I've shown you before. Just a simple tag, leaflet map. I give it a name, a callback to get a handle on the map. And in JavaScript, I can then load the GeoJSON in Ajax and add it to the map with a simple line. And that's it. The map shows up with a building layer that can be interactive and can be shown to the world. But that's not all. I also developed a set of tools to edit the geometries and define some geographic forms using Leaflet and not OpenLayers 2, which comes by default with Django. And the API is respected. I mean, there is nothing new. It's very simple to use. You define the form as usual, override the widget, and you've got a little map to edit the geometry columns in the geometry field. There's also a Leaflet admin site base class. You just register your class with this Leaflet GeoAdmin, and it integrates in the Django admin site, and you can edit your objects if you want. And there is a simple drawing tool, and you draw like you would be 3 years old, and draw the shapes and save, and that's it. It's a very ugly screenshot, but yeah, that's the drawing tools. Of course, it validates the data and gives you the proper tools depending on the geometry type. So that's it. So the conclusion is, cartography is simple. Anyone can do web mapping. You just have some special data types in your database. You just follow the Django convention using the tools available in your preferred framework. With a very few lines of code, you get your map showing up, and you can edit your geometries. So there is no reason to be scared or whatever. But it can also be hard because the volumes of the data can be huge. The format, the vector format can be quite verbose and quite heavy. So you have to control the precision of your data, and of course, as usual, control the caching. You will have to use the decorators available in Django to cache depending on last modified objects and pragma directives you want to send to the border, so that the caching will be tuned and very fine-grained to prevent users from downloading loads of data from it. And usually one of the problems I meet on my daily work is that the data available is very far from the user stories. So you have to model your data in a proper way so that the database doesn't work too much. So you have to like denormalize and optimize queries and whatever. But that's only when the data is huge. If you most of the maps I see, they just put markers on the map, some pop-ups, and you shouldn't need the whole stack for that. Just use the GeoJSON fields I've shown you, and they integrate automatically with the leaflet editors. So you can have very simple maps with geometries with a SQLite database, no GIS, nothing. So if you want to show on a map the positions of your company's location or Django developers, then maybe you don't even need BuzzGIS or you don't even need huge technology, just simple stuff. Cartography can be simple. That's it. I hope it was not too